Today, we're diving into a fascinating new patent that could completely change how we think about food quality. We're talking about a non-destructive way to evaluate shrimp by looking at the water hidden inside. Let's get into it. You know the feeling, right? You buy a bag of frozen shrimp, you're picturing this perfect, firm, tasty meal, and what you actually get is just mushy and disappointing. Well, that inconsistency is a massive headache for the food industry. How do you really know what you're getting before you cook it?
All right, so here's how we're going to crack this quality mystery today. We'll kick things off with the unseen problem in shrimp quality, then look at the new tech that can actually measure the water inside. After that, we'll learn how to read its data graphs, decode the two key indicators, J1 and J2, and finally, see how this whole thing could totally change the future of food production. Okay, so here's the absolute heart of the issue. The biggest thing affecting a shrimp's texture, its flavor, everything. It's not just how much water it has, but how that water is being held inside its structure. That's the invisible problem that makes all the difference between good shrimp and bad shrimp. For years, the industry has pretty much relied on the same old playbook. You know, they might dry the shrimp out to measure water content, squeeze it in a centrifuge to see what comes out, check how much water it loses when you thaw or cook it, or they'll use a machine to test its texture, and of course, the classic human taste test. But, and this is a big but, these old methods have some major drawbacks. For one, they're destructive. The shrimpy test gets ruined, so you can't sell it. They're also really slow and take a ton of effort. And maybe worst of all, a lot of them are subjective. What one person thinks is perfect texture, someone else might disagree. In a class-paced, modern food factory, that's just not going to cut it. And that brings us to the really cool part of this patent, the new solution. It's a technology called low-field nuclear magnetic resonance, or, much easier to say, LFNMR. Now, the easiest way to wrap your head around LFNMR is to just think of it as a small, specialized MRI machine, but designed specifically for food. It uses magnetic fields to get this incredibly detailed picture of the water inside a shrimp, all without ever having to cut it open or damage it. It's pretty amazing. And here's the key. The goal isn't just to find out how much water there is, it's to figure out the state of that water. How tightly is it bound to the shrimp's protein? Is it locked in place, or is it just kind of sloshing around freely? Because that mobility, that's the real secret to predicting quality. So this machine spits out data, but what does that data actually look like? Well, this is where we get to the core of this whole thing, learning to read something called a T2 graph. Think of it like a unique water fingerprint for every single shrimp. So the main result you get is this T2 distribution curve, and the shape of this graph tells you a really detailed story. It shows you all the different states of water that are inside that shrimp at that moment, from the water that's super tightly bound to the water that's most mobile. And the patent lays out this brilliantly simple, standardized way to analyze this fingerprint. First, the machine generates the curve. Second, you draw two fixed boundary lines on the graph, which are called T2A and T2B. And third, those lines automatically chop the graph up into three separate areas, which we'll just call A1, A2, and A3. Each of these areas tells you about a different kind of water. Area A1, that's the good stuff, water that's really tightly bound to the proteins. It's stable. Area A2 is kind of in the middle, moderately bound, but Area A3, way over on the right, that's the free, mobile water. This is the problem water, the stuff that leads to drip loss and that mushy texture nobody wants. Okay, now we get to the real stroke of genius in this invention. Instead of having to be an expert at reading complex graphs, this system boils all that information down into two simple, powerful numbers that give you a crystal clear verdict on quality. So the first indicator is called J1. The formula is actually really simple. You just take the area of that problem water, A3, and you divide it by the total area of the whole graph. So what J1 is really telling you is what percentage of all the water in the shrimp is that bad, free-floating kind. Then we have the second indicator, J2, which gives us a different but equally important angle. This time we take that problem water area, A3, and divide it by only the good water areas, A1 plus A2. So J2 tells us how much the water is skewed towards being free and mobile. Is there just a little, or is it starting to overwhelm the good, stable water? And here's why the patent insists on using both of them. It's so smart. J1 gives you that big picture overview, while J2 gives you the critical ratio or skew. Using them together makes the whole check way more robust and less likely to give a false reading, which makes the final decision much, much more reliable. And so the final judgment call is beautifully simple. For a shrimp to pass, its J1 score has to be within the acceptable range, and its J2 score has to be within its acceptable range. If even one of those numbers is off, the whole batch fails. That's it. It's a clear, objective, black and white quality gate.
Okay, so let's zoom out for the final section and look at the big picture here. What does a method like this actually mean for the food industry? How could it really change things?
I mean, the difference is just night and day. We're going from quality control that is destructive, slow, and totally subjective to a new process that's non-destructive, super fast, and gives you objective, repeatable numbers every single time. It's a complete game changer.
And the benefits are just enormous. Food producers can now set up standardized quality gates for everything they buy and everything they sell. They can get way better consistency from one batch to the next. Inspections that used to take ages are now lightning fast. Waste goes down because you're not destroying samples. And the results are totally objective and easy to explain. At the end of the day, what this patent really creates is a reliable, standardized checkpoint. It doesn't matter if you're inspecting raw ingredients coming into the factory or doing a final check before you ship a product out. This method gives you a level of certainty that was basically impossible before.
And you've got to wonder, right? This patent is all about shrimp, but just think about the possibilities. The source material itself hints that this same idea, analyzing water states, could work for other seafood, like fish, or even fish roe. What other foods could use a quick, non-destructive quality check like this? It's a huge open question.
So really, when you boil it all down, this is what's happening. A complex scientific measurement gets turned into a simple fingerprint graph, which then gets distilled into two key numbers that deliver a clear pass or fail. It's just a perfect example of how innovation can bring better, more consistent quality to the food on our plates. It really leaves you with a final thought, doesn't it? The next time you're about to eat a shrimp that's perfectly firm and delicious, you might just catch yourself wondering, hey, did this one pass its J1 and J2 test?